So, now let us come to a very famous Maxwell's theorem, that is equipartition theorem. This is very important, derived from statistical thermodynamics. So, Maxwell derived a theorem according to which to each degree of freedom on an average half kT amount of energy is associated. So, this theorem is called equipartition theorem. That is, the half kT energy is equally partitioned, divided among all the degrees of freedom. So, what does it mean? So, you see monoatomic gas molecule. So, let us take an example of monoatomic gas molecule. According to equipartition theorem, the energy will be the number of degrees of freedom into on an average half kT energy. So, this is the expression for the energy of a molecule. So, for a monoatomic gas, the number of degrees of freedom, you know, it is 3. So, 3 by 2 kT. Let us recall, this is what we derived in the kinetic interpretation of temperature. For a diatomic atomic gas molecule that is non-vibration type, the energy will be equal to F into half kT. So, that is implies the degrees of freedom is 5 by 2 kT. This is for a diatomic gas molecule. Diatomic gas molecule vibration type means where at higher temperature I can take vibration. This E will be F into half kT, that is here 5 plus 2 more, that is 7 by 2. We have 7 by 2 kT energy associated with a diatomic gas molecule at a higher temperature. So, we have now polyatomic gas molecule will have energy E equal to, at lower temperature, that degrees of freedom will be 3 translational and 3 rotational, that is 6 by 2 kT, and at higher temperature E will be equal to 2 more vibrational states will be. So, 6 plus 2 8 by 2 kT energy is associated. So, now the equipartition theorem tells that how much each molecule will have degrees of freedom. So, now what if we say that a monoatomic molecule is, now we can understand what is the meaning of the degrees of freedom and this equipartition theorem. So, you see, I claim now that this is half mvx square, half mvy square as half mvz square. This is the energy of a monoatomic gas molecule. Now, you just imagine that this energy has 3 pockets. First one this, second one this one, and the third one this one. That means, the molecule can have 3 pockets of energy, each can store half kT of energy. That means, each pocket is available. So, more and more pockets That means there are more and more number of ways in which the energy can be possessed by the molecule. Thus, the equipartition theorem tells that all these kinetic energy terms, degrees of freedoms, can equally store energy, and the energy stored is half kT though. So, they are equally capable of storing energy, and equal amount of energy will be distributed into them. And so, that more and more energy means more the degrees of freedom. So, now I can relate the total internal energy of a gaseous system with the degrees of freedom and the total energy with the help of equipartition theorem. And after calculating the internal energy, we will see how the specific heat of the gas will depend on this degrees of freedom. So, now let us come back to our internal energy of an ideal gas. So, consider an ideal gas which has molecules of F degrees of freedom. So, the internal energy of that gas is the total number of molecules it has into the total energy of this energy of each molecule. So, energy of each molecule is F is the degree of freedom and half kT, this is the energy of each and every molecule on an average. Total number of n molecules. So, we can write this function n is n into again Avogadro number, n is the number of moles, F is the degree of freedom, half, K is universal gas constant by Avogadro number into T. This cancels out. So, the expression for internal energy becomes n into F R by 2 T. So, this is the expression for internal energy. Now, let us see. So, we have type of gas, then we will write degrees of freedom, then here we will write delta U. So, number 1, let us see monoatomic gas. So, monoatomic gas we have seen 3 degrees of freedom. So, 3, that is 3 nRT by 2 will be its internal energy. So, if we have a diatomic gas, non-vibration means at low temperature, it has 5. So, this is 5 nRT by 2. If we have third diatomic gas at higher temperatures, where degrees of freedom will be 7, 2 more, then it will be 7 nRT by 2. Next, polyatomic gas at lower temperature, that is also non-linear type. Then 3 plus 3 6, we have 6 nRT by 2, that is we will write this as 3 nR. And again if we have polyatomic gas with at higher temperatures, so plus 2, 6 plus 2 is 8, 8 by 2 means 4 nRT. So, these are the internal energies for different type of gases.